In this lecture, you'll learn how you can reconstruct the original data from its principal components. We spoke about this earlier when we design an autoencoder with a hidden layer with linear neurons and we use the mean square error as our reconstruction loss function. We said that the autoencoder performs principal components analysis. That's exactly what we'll see in this demo. We'll use some stock returns data that we'll read in from a CSV file and calculate its principal components using a Python library. We'll then calculate the principal components using TensorFlow and an autoencoder. When we compare the two, we'll be able to prove that autoencoders with a linear hidden layer and the mean square error as a reconstruction loss performs PCA. All of the import statements that you see here are the same except for one. Notice that from the Matplotlib library in the MLab namespace, we import the PCA class. This is the Python library that will allow us to perform principal components analysis on stock returns data without using a neural network. This will serve as the baseline with which we compare the autoencoder output. I've stored the CSV file, which has the monthly closing prices for a number of different stocks here in my current working directory, right next to where my code is. Now, if you want to use the same file for your analysis, you can find this at this Google Drive folder. All the other data sets that we've used in the demo so far are also available in this Google Drive folder. This CSV file contains the data that I've downloaded from the Yahoo Finance website, and this contains the monthly closing price for these stocks. And this is over the last 10 years. So we have 12 months for a year, and over the last 10 years, 120 rows of data. We have data for the companies Adobe, Chevron, Mondelez International, Netflix, Oracle, and Starbucks. Read in the CSV file using pandas pd.read_csv and specify the name of the file. The data frame is called prices. When you examine the data, you'll find the closing prices, but you'll find that the date field has been read in as a string. It's not in date format. The rows are also not in any order. The dates are spread around at random. The data that we have available in this data frame is the closing prices, but what we are really interested in calculating is stock returns. Now, stock returns is the increase or decrease in price month on month. Those are monthly returns, and given that we have the monthly closing prices, we want to calculate monthly returns. In order to calculate monthly returns, we require that all records be sorted by date. And the very first step to that is to basically format the date column as a date rather than a string. This we do using the pd.toDateTime function. We don't specify what format the date is in. We simply say infer datetime format and set it to true. Next up, we want to sort all the records by date so that we can go about calculating returns. Typically, when you work with stock data, we work with returns because returns are a good way to compare across years how a stock has performed. The absolute price may swing wildly and will be different from stock to stock, but returns will allow us a basis for comparison across stocks and across years. If you explore the data frame now, you'll find that the records are now sorted in ascending order of date, and the date column itself has been formatted as a date and is no longer a string. Now, before we perform principal components analysis, let's simplify our lives a little bit. We have data for around 6 or 7 stocks. We'll just choose 3 of these stocks at random: Adobe, Mondelez International, and Starbucks. Reducing the number of columns allows us to examine the data, makes the data more tractable for manual examination. Next, we calculate the returns. Fortunately, we don't have to do any heavy duty math here. That's because Pandas provides a built in function allowing us to calculate returns. So, for all columns which are of float or int64 type, simply call %change on the column to get return values. Now, the very first month for which we have data, that is January in the year 2007, will not have any return value associated with it because we don't have any data for the previous month. So, there is no comparison to get returns, which is why we leave that one record out of our calculation. When you examine the data now, you'll see that it looks very different. All our closing prices have been replaced by return values. Our data set currently has around 120 rows. There is one row for every month over the last 10 years. Let's simplify this data set a little bit. We don't need so much data in order to show that PCA can be performed using autoencoders. We'll just use 10 rows of data. This allows us to examine it manually and makes things very simple. We now have a very small and manageable matrix on which we'll perform PCA. It has 10 rows and 3 columns for 3 different stocks. Before we perform principal components analysis, we'll normalize our data. We use the standard scalar library class from sklearn.preprocessing. Standard scalar will normalize and scale the returns so that they're centered around 0. All returns will then have the same range. The sklearn library is simply scikit-learn. This is a very popular machine learning library implemented in Python and widely used for many standard ML algorithms. This library can be installed on your machine using pip install. Instantiate the standard scalar class from scikit-learn and then call the fit transform method on it and pass in the array that we want to normalize. Normalization typically involves subtracting the mean of all the data and dividing all the data by the variance so that they're centered around 0 and are in the same range. Once this is done, you can see what the normalized data looks like, and it is on this data that we'll perform principal components analysis. And this is super simple because we have Python libraries that just take care of this for us. We use the PCA library from Matplotlib, pass in our normalized array, and set standardize equal to false. Now, standardize is equal to false here because we've already scaled and normalized the data ourselves. The reason we chose to normalize the data ourselves was because we are going to feed this array into our autoencoder as well, and we wanted it normalized before it goes into the autoencoder. The results variable holds the principal components and some other details. Result.fracs is a variable that shows you how much each principal component contributes towards the overall data. Fracs holds the proportion of variance of each of the principal components. If you look at the numbers on screen, you'll see that the first principal component contributes 61% of the variance, the second 28%, and the third around 10%. They all sum up to 100%. So if you just use the first two principal components, you've captured 90% of the information in the original data. The principal components of our original data are held in results.y. You can see that the number of dimensions in the original data is equal to the number of principal components that we have. The original data had 10 records, so we have 10 rows here, and for 3 different stocks, we have 3 columns here. You can compare these principal component values with the original scaled array, and you'll see that they're very different because the principal components are basically projections of the original data in PCA space. Results.weight will give you the weight vector. This is the vector used to project the original data into PCA space. If you use this weight vector on the principal components, you can reconstruct the original data. So this weight vector matrix multiplied by the principal components will get you the original data back. And you can see this for yourself right here by performing a simple dot product on results.y and results.weight. If you compare this result here, you'll see that it's equal to our original scaled array. I'll print out the original scaled array right here. Here is the dot product on top and the scaled array at the bottom, and you can see that the numbers are the same. This is how we use the weight vector along with the principal components to reconstruct the original data. Now let's perform principal components analysis using an autoencoder. These are the parameters for our autoencoder neural network. The number of inputs is equal to 3 because we have 3 columns in our input data. The number of neurons in our hidden layer, that is our codings layer, will be 2. This is the reduced dimensionality or the constraint of our autoencoder neural network. And the number of outputs is equal to the number of inputs. Remember that the neurons in the output layer should be equal to the number of neurons in the input layer. Let's reset the default session graph so that we start anew and set up a placeholder X to receive the input stock return data. The hidden layer is a dense layer with no activation function. It's a linear layer. This is a layer with just two neurons. The output layer is also a dense layer. This has three neurons equal to the dimensionality of the input, and it takes as its input the output of the hidden layer. Remember that in an autoencoder, the dimensionality of the output layer should be equal to the dimensionality of the input layer, which is equal to the number of dimensions in the actual input. The loss function for an autoencoder is the reconstruction loss, because what the autoencoder tries to do is to reconstruct the input. In order for the autoencoder to perform principal components analysis, this loss function should be the mean square error. Notice that we don't use any labels. In fact, we don't have any labels. We simply compare the outputs to the input X. This is our autoencoder neural network for PCA. And then things here should be very familiar to you. We set up our Adam optimizer and the training operation, which minimizes the reconstruction loss. Instantiate a session and run training for 10,000 iterations. Each iteration is an epoch. We don't have batches here because our data set is very, very small. Input that we fed into this neural network has a dimensionality of 3. Remember the 3 columns for the 3 stocks. The hidden layer has just 2 neurons. That means the autoencoder was forced to represent the input data in 2 dimensions. It chooses 2 of the most significant dimensions. The output that the autoencoder reconstructs is from this reduced dimensionality encoding. It doesn't have the entire original data, it has the data represented in reduced dimensions, 2 dimensions instead of 3. Evaluate this reconstructed output and print it to screen. The training process should run through very quickly, and this is our reconstructed output. Now, because this output has been reconstructed from lower dimensions than existed in the input, this isn't a perfect match for the input that we fed into this neural network. What this output represents, though, is the input reconstructed using two principal components. If you remember, the input layer had 3 neurons, as had the output layer, but the hidden layer, the codings layer, had just 2 neurons, which means it could use just 2 principal components, and these 2 principal components were used to reconstruct the data. Let's prove this. If you remember, just a little while ago, we performed principal components analysis using the Matplotlib library. We also know that we can use the principal components and the weight vector to reconstruct the original data. Now, instead of using 3 principal components, let's just use 2 principal components and the corresponding weight vector, calculate the dot product, and see what the reconstructed data looks like. We use the first 2 principal components stored in results.y and the weight vectors for those stored in results.weight. And if you look at the result, you'll find that it looks very familiar. The reconstructed result using the first 2 principal components is exactly the same as the output of our autoencoder neural network. And this result proves that our autoencoder, set up with linear neurons in its hidden layer and with the mean square error as its reconstruction loss, simply performs principal components analysis. While generating principal components, we use a weight vector to project the original data in PCA space. Now, if you take the principal components matrix and multiply it by our weight vector, we get the original data back. The weight vector is what we use to reconstruct the original data from its principal components.